We'll now discuss how the operating system uses these resources safely. So not only must resources be used efficiently, but they must also be used safely. That doesn't mean an operating system must prevent users from sticking their fingers in the power supply and getting electrocuted. It's not going to be able to do that for you. But instead, it's the job of the operating system to prevent programs or users from attempting operations that would cause the computer system to enter a state where it's unable to do any work. A frozen state, we would say, or freezing the system, where all useful works just comes to a grinding halt. To see how this can happen, let's imagine a computer system that has one laser printer, a data file which we'll call D, and two programs A and B. Program A wants to load data file D and then print it on the laser printer. Program B wants to do the same thing. So we get a following list of requests for both programs A and B. So A would first say, get the data file D, then get the laser printer, and then print the file. Whereas program B is going to do the similar request, it's just the order is a little different. So program B is going to first ask for the laser printer, and then it's going to ask for data file D, and then it's going to print the file. If the operating system satisfies the first request of each program, then technically A owns the data file D, and B has the laser printer. So whenever A asks for ownership of the laser printer, it's going to be told that the printer is currently being used by B. Likewise, if B asks for the file, it's going to be told to wait because A is currently using the file. So what we have here is that both programs are waiting for the other one to finish. And let's just face it, this isn't going to happen. They're not going to free up because A is not going to let go of the file until it's able to print it, so it needs the printer to do that. And B isn't going to let go of the printer until it has the file to actually print. So they're just kind of stuck. The situation that we just described is an example of what we call a deadlock. So formally speaking, a deadlock occurs when we have a set of programs where each of which is waiting for an event to occur before it may proceed. But that event can be caused only by another waiting program in the set. So in our example, we have A waiting for B, and we have B waiting for A. So we have a deadlock. So how does the system actually handle these deadlock conditions? Well, there are two basic approaches for handling deadlocks. We have what's called deadlock prevention, and then we also have deadlock recovery. In deadlock prevention, the operating system uses resource allocation algorithms that prevent deadlocks from occurring in the first place. So in the example of the two programs simultaneously requesting the laser printer and the data file, the problem is caused by the fact that each program has a portion of the resources needed to solve the problem, but neither has everything that it requested. So to prevent this, the operating system can use the following algorithm. If a program cannot get all the resources that it needs, it must give up all the resources it currently owns and issue a completely new request. In other words, the algorithm is saying is if you cannot get everything you need, you get nothing. So if we had used this algorithm, then after program A required the laser printer but not the data file, it would have had to relinquish ownership of the printer. So now B could get everything it needed to execute, and then no deadlocks would occur. Now let's say we do get a deadlock to happen. Let's just face it, it is going to happen. There is no way to 100% guarantee prevention of deadlocks. We're going to get deadlocks. So whenever this happens, we need to be able to recover from it because we don't want the system to lock up. That's never good. So we need a way to fix that. And using our example, what we could do, and this is just one possible technique, is we could select one of the programs that's part of the deadlock and just have it free all of its resources. So like we can just say pick A or B, and then whatever resources it's holding, free it up. And that way the other program could get the file or the printer and finish its job. Now, how do we go about selecting the program? We're not going to worry about that in this class. This is just to show that we do have a way of recovering from deadlocks by having the processes that are locked up free its resources.